So today's lesson 6, single slit diffractions. So the last class we talked about the young double slit. And if we review quickly some of the diagram and kind of the key thing is I need you to know the difference between a single slit and a double slit. Okay, so let's just review a double slit. Okay, double slit basically would have kind of these small opening. We call it S1 and S2 for source 1 and source 2, but really it's just one source, but it has like two really small slits that are in between them. And the distance between the two slits, we call it D. Okay, so we call this D, the distance between the two slits. Okay, then what happened is we then kind of measure the distance to a screen. Okay, so the screen distance, we call this the L. Okay, the distance from wherever your point source, your slit, all the way to wherever the screen is. And then in there, we measure the bright and the dark spot. The spot in the middle are always bright. Okay, there is always a constructive interference right at the middle. Okay, that is the dark. Okay, between the first dark line, we call it n equals to 1, and the first dark line, we also call it n equals to 1. And then there is the next dark line that will come here. This is n equals to 2, and this is n equals to 3. This is n equals to 2 and n equals to 3. The first thing you need to remember is that the distance between any dark line, we call it delta x. Okay, we're always talking about the nodal line, delta x. Okay, and so that's a delta x, and then between any nodal line, that's a delta x. Okay, and we always would have a line. So I think the biggest interesting thing is you need to be careful that from the center to wherever the line is, that is x1. Okay, so from wherever the center to the dark line, this is x2. So you have to be careful with the wordings, okay? And so on and so forth. And this point right in the middle, we call this the central maxima. Okay, so basically the bright right in the middle. Okay, the central maxima in a double slit equals to delta x. Okay, the central maxima. So if I take the length of the dark, between the dark and the dark right in the middle, it's called delta x. And they're the same as every other bright line and dark line, the distance with it. So all of them are delta x all the way along. Okay, so I don't know if that tells the wording, so just be careful. And the last thing that we also talk about is if I have a line right from the middle here between the 2-point source and I connect it to any dark line, I'm going to do it in here. Okay, I'm just going to pick the second point. If I have this straight line and I connect it, okay, this line, this is angle theta 2 because it's connecting to the second line, and that's what the angle represents. It's from the center line to the line that is connecting to the nodal line. This is theta 2. So if I connect it up, say to, I don't want to draw it all because it'll be too much. But if I say connect the first dot, like n equals to 1, then that from that center point to the purple point there, those will be theta 1. Okay, so those are the wordings. Okay, so now here are two pictures. One that is an interference between a young double slit experiment and then an interference pattern of a single slit diffractions. And if I can give you this to you on the test and I say, hey, tell me which one is single slit and which one is double slit, you should be able to tell. Based on what I talked about just now, okay, if you go back to this picture, okay, the central maxima is what you can tell to help you tell if something is a single slit versus double slit. We already talked about that basically delta x are exactly the same between every single dark line in a double slit experiment. So if I point you to that, hopefully you're able to understand that this is a picture that is actually a double slit. Okay, The reason for that is if you take a look at the dark line, in between every dark line, do you see their equal distance all the way across? But in this one, I would have this, like they're all the same with the exceptions of the center. Okay, this magnified one, it's actually an interference based on the single slit. So that's one way to tell. Okay, and the other way that you can tell, there is a chart in here. Okay, the other way that you can tell is that between a young double slit, you have most of the maxima which are the same brightness, but then with a single slit interference, you can actually see that the secondary, meaning the later on, not the middle ones, they decrease in brightness very significantly. Can you tell that from this picture? The brightness right in the middle for this guy, it's a lot stronger than all the other ones. I know that at the bottom picture, it still looks kind of dimmer and dimmer as it go, but definitely it's a lot more obvious when we take a look at this. This is a lot brighter than the other one. Okay, so that's why if you go back to the chart, so this is something good to know. Okay, light pass through a single narrow slit. So we're talking about single slit. Usually this is how wide it is. There are diffractions that are happening, just like the single slit. The central maxima in this time, it's actually a super bright region in the middle. And we call the secondary maxima, meaning the other ones, like the second bright line, the third bright line, and so on and so forth, we call them the secondary. And what we have noticed, as I was talking about, is that with the young double slit, you have all the maxima should all have the same width, including the center one. But then with a single slit, you would actually notice that the central maxima is actually double the width for any other brightness. Okay, and remember we measured bright and bright between two dark lines. Okay. All right, and here's just explaining. If this goes straight through, we're going to have bright lines. But then as it started to go in an angle of a phase difference of lambda over 2, you're going to notice the first possible dark line. And keep going. Second one, when it goes to 3 over 2 of a wavelength of a path difference, you notice a bright line. And so on and so forth. The scientists are being able to see repeating patterns, and the general pattern that they found for any dark line is that sine theta n is n times lambda over w. So in this case, the w is basically the width of the slit, of the single slit. So instead of calling it d, the distance between the two source, we call it the width of a single slit. All right, so notice the wording, okay? So we have delta y. Oops, we have delta y like we did before, but instead of x, we call it y. We still have the dark line and the dark line, so these are the destructive interference that are happening, and those are the dark, dark, dark. Okay, the middle one, it's the center, so this is the center, the central maxima, and that's the bright spot. And you would notice that it actually is double the width. So different from what we did before. We said everything was the same width with the double slit, but with the single slit, you actually have 2 times the delta y. So just be careful of the central maxima when we're dealing with the single slit experiment. Okay, so wordings wise, it's pretty similar. From the center to the first dark line, we call it y1. So this is the center, is y1, and then the next one is from the center to the second is called y2. But notice that this is the same distance, because if you remember, I don't know if you remember, but let's just go back to here. Okay, all the delta x, if you take a look at it, x1, it actually equals to half of any of the delta x, just x1 though, okay? And then x2, if you actually take a look at it, it's 1.5 delta x, right? But in a single slit situation, you would have all of them the same. So y1 is equals to delta y, and y2 is also is equals to 2 times the delta y. Okay, because this one is delta y. This one is delta y. All right, so then the relationship when I shine it on the screen, that is L amount of distance. So this is the screen. So this is where the screen is. And then if I measure what delta y is, delta y had the same meaning as before. Delta y is the distance between consecutive nodal line. So dark line and dark line. Okay, just be careful with except the middle, right? But we'll do example that covers the middle one. Okay, L is the distance from the screen. Lambda is the wavelength of the light wave, and W, as we talked about just now, is how wide the width is, right? The width of the slit. Okay, and then lambda's wavelength of light. All right, so let's read this. The light of the wavelength 750 nanometer passed through the slit of 1 times 10 to the negative 3 meters wide. How wide is the central maxima in terms of angle? And calculate the absolute width on a screen that is 20 centimeters away. And then what is the separation of the adjacent minima? Okay, all right, so lots of wordings. Not meant to be hard, but you need to know your wordings. Okay, so wavelength of light is lambda. Lambda is 750. Nano means -9. So I'm just going to put it in. If you want to say this really is 7.50 times 10 to the -7, right? I don't know if you know that that's the same. I'm sure you do. Okay, and then they tell you the width. So this is a single slit, a slit. So this is single slit. The symbol we use is W. And they tell you that the width is 1 times 10 to the -3. How wide is the central maxima? By the angular. So they want you to find out what is angle theta, right? So go to the equation with angle theta, right? Theta is sine. And this time you're going to find number 1. So let's get going, all right? So part A, I would like you to calculate what is theta 1. Okay, so the equation is sine theta n equals n lambda over W. So sine of theta n, theta 1 is what I'm looking for, is 1 times the lambda, which is 750 times 10 to the 9, -9. And then the width is 1 times 10 to the -3. Punch it in your calculator. 1 times 750 exp -9 divided by 1e -3. I got a value of 7.54. So to solve for theta 1, I have to go shift sine of the answer I got. So 0.043 degree. Okay, if you tell me that's the answer, you're going to lose a mark. Okay, I need to know both sides. Okay, I need you to tell me basically theta 1 and theta 1 that you understand that, oh, the central maxima is double of it. Okay, so the actual central, the angular width is going to be 2 times the theta 1. So times it by 2, so I got something like a 0.086 degree. I know usually I say degree, just don't worry about it. Round it to the whole number. This one's super small. Just leave it with the proper signics. Okay, part B. Part B tells you now have a screen that is 20 centimeters away. I know screen means L. 20 centimeters. Please change that into meters. That is 0.2. And they're asking you what is the absolute width. So you're going to have to find the actual width. So what is the actual width? That is your X1. Ooh, nice fancy pen. Okay, Y1 is what I'm looking for. But remember, I need it on both sides. So that means I'm going to have to find the central maxima is going to be 2 times the y1. So n lambda over w is equal, all right, I need y1. Okay, so the y1 actually refers to the y1 over L because they're combining this equation with the, remember the sign thing, right? That's the same thing, so that's why it's y1 over L. So 1 times lambda divided by w equal y1 over L. So 750 divided by 1 to the negative 3. Oh no, I should, yeah, and then times 0.2. So y1 is 1.5 times 10 to the negative 4. So the central is going to be 2 times of the y1. Multiply that by 2. So 3.0 times 10 to the negative 4 meters. That's how y, like that's, so what that means is what we've done just now is we have done from here to here. That's a central, the absolute width of the central. All right, last one. They are asking you what is the separation of the adjacent minima, okay? In other words, they want you to find delta y. But they said don't do the central. Like don't worry about the double of it. Okay? So I would like to find delta y. So the equation for delta y is right here. Lambda over w equals delta y over L. Lambda over w equals delta y over L. L is 0.2, so cross multiply 750 e negative 9 times 0.2 divided by 1 e negative 3. So each of the delta y is 1.5 times 10 to the negative 4 meters. And that, does that make sense? That it should be half of the central because we already talked about it. Single slit would be double, right? Okay, last one. Light shines through a rectangular hole in a narrower in the vertical than horizontal. Narrower in the vertical. So for this question, okay, let's read this again. Light shines through a rectangular hole that is narrow in the vertical direction. So the picture looks like this. Okay, narrow in the vertical direction than the horizontal. Do you expect light to diffract more in the vertical direction or in the horizontal direction? All right. So go back to your equation. Okay, so let's just take a look at, so diffraction, the word diffract more, if I have a delta y that is high, it diffract more, meaning it got spread out more. Okay, so let's take a look at equation. I have the equation for delta y is lambda over w equals delta y over L. Okay, L is the screen. That's a constant. So I'm going to highlight things that are constant right now for me. Okay, this is a constant. And that's also a constant. The wavelength of light, we're not changing. We are trying to look at the relationship between delta y and w. Because w is basically what we're looking at. So if I have something that is if I'm looking at vertically, okay, if this is your w, versus if I look at horizontally, let's change color. Something that's horizontally, if I'm shining the light through horizontally, the delta, your W is this wide. Your width is that wide. So they're asking you, with a bigger W or a smaller W, would it yield a bigger Y or a smaller Y? If you need to, you can rearrange your equation. Most of you don't like racial thinking questions. You guys always just like punch it in the number, get an answer from me. Okay? If I look at delta Y on its own, delta Y is lambda times L over W. If I want a big delta Y, would I divide it by a big number or a small number? I'm going to ask this question again. If I want delta Y to be big, do I divide W as a smaller number or a bigger number? Do you see how the smaller the W, the larger the Y is, because I'm dividing by a smaller number, right? So that means the vertically, which is the smaller number, this one will give you a higher delta Y, meaning larger diffraction. Vice versa, horizontally, if I'm dividing by a big number, then my delta Y, meaning diffraction, will go down. Okay, diffraction will go down since my W would increase. I am dividing by a bigger number. My delta Y would decrease. Okay, so if I were to draw the wave, that means I'm going to have bigger diffraction this way, but smaller diffraction this way. So my dark line would be closer together horizontally. All right, B. Should a rectangular loudspeaker at a stadium be high and narrow or wide and flat? So if I'm setting up sound wave, okay, but it's still wave. So should my speaker, if I want a stadium, okay, do you see how stadium, like I have the seats here, I have to go all the way. Like I would like to be able to reach my sound horizontally this way. My speaker should be mounted this way so that I would have a bigger diffraction across horizontally. Okay?